Let's take a look at mass spectroscopy, and one of the main objectives of this screencast is to learn how to calculate the average atomic mass of an element given the results of a mass spectroscopy. Okay, so that's where we're headed. Given the results of a mass spectroscopy, calculate the average atomic mass of an element. Okay, but first, let's review a couple of things. Subatomic particles. Protons and electrons are the only particles that have a charge. Remember, protons are positive, electrons are negative, neutrons are neutral. Protons and neutrons have essentially the same mass. Here is the two masses. They're pretty much taken to be one atomic mass unit. Electrons have a very small mass. As a matter of fact, they're about 1/2000th of a proton or a neutron. So we typically ignore the mass of an electron because it is so much smaller than that of a neutron or a proton. Now let's talk about the nuclear symbol for an element. Symbols of the elements are either one or two letters. We're going to take a example carbon, which is a capital C. Sometimes you will see the element with a small number written in the bottom left. That is known as the atomic number. It is the number of protons and the number of electrons for a neutral atom. You remember that this is for a neutral atom, because in a neutral atom, protons are equal to the electrons. The symbol for that atomic number is a capital Z. The number to the upper right, it's still the left, the upper left, just seeing if you're being awake, is known as the mass number. The mass number is the number of protons plus the number of neutrons. You should remember this. And that is for a specific isotope. Mass number is for a specific isotope of that element. It is not on the periodic table. So here we have 4 isotopes of carbon. Each of them, hopefully you notice that they all have the same atomic number. That's what makes it carbon. It has the 6 protons in the nucleus. But all of them have a different mass number because they differ in the number of neutrons. Okay, so these all, because they differ in the number of neutrons, have different masses. Again, these are all isotopes. They have different numbers of neutrons. You can determine the number of subatomic particles in each particular isotope as long as you are given the mass number. This is another way of writing the nuclear symbol. All of these are the mass number. If you are unsure of how to do this, try, and then come into class and check with me if your chart is correct. On second thought, let's run through this. All right, we'll do oxygen together, and then I'll pause it, fill in the chart, and then come back. All right, so for oxygen 16, from the periodic table, the number of protons in an oxygen atom are 8. Oops. Oh, geez. Oh, geez. Here we go. Sorry about that. Okay, number 8, since it's neutral, it also has 8 electrons. Its mass number is 16. That has to be given. Remember, it is not on the periodic table. To get the number of neutrons, it is 16 minus 8. Number of neutrons is also 8. Go ahead and fill in the rest of the table. Okay, so here is the finished table. Pause if you need to double check your answers. Okay. All right, so let's take a moment and actually look at a mass spectrometer. All right, atomic and molecular masses can be measured with great accuracy with one of these. There are several parts to this mass spectrometer, and we'll look at this in a little greater detail. I think there's a better slide coming up. This is an actual mass spectrometer that looks very impressive as a piece of equipment. This is also a mass spectrometer, not as impressive. Okay, so what happens in a mass spectrometer? The sample is injected into the mass spectrometer here. There's a heater that vaporizes the sample. An electron beam ionizes the sample in this region, and then the particles are accelerated through here. There is a magnet, okay, and that serves to deflect the particle beam. This region here is a magnetic field separating particles based on a mass to charge ratio. So it's a charge beam coming through here, the lightest of which is on this side, the heaviest is on this side, and then there is a detector on the end of the mass spectrometer. Same thing, just a little bit more detail. It is a vacuum pump. Oops. I don't know what, oh. I don't know what, here we go. Jeez. Sorry guys. So there's a vacuum pump, so there is no other particles in this system for these isotopes to collide with. That's kind of an important thing to note. So, why do we use a mass spectrometer? Well, it's used to measure relative masses of isotopes and also to find the relative abundance of those isotopes in a sample of an element. Again, another schematic of a mass spectrometer. So, when charged particles pass through a magnetic field, the particles are deflected by that magnetic field. The amount of that deflection is going to depend upon the mass to charge ratio of that charged particle. Again, there's 5 stages of that mass spectrometer. There's a vaporization phase, puts the sample into the gaseous form, either from a solid or a liquid. The next is the ionization phase, and in this, the sample is actually bombarded by a stream of high energy electrons. The interesting thing is those electrons actually knock the electron from an atom, so it actually produces a positive ion. So the ionization phase produces a positive ion. That positive ion is then put through an electric field, and that accelerates the positive ion towards the magnetic field. those ions are put through a slit in the material to produce a narrow beam of ions. That narrow beam of those ions are then deflected by the magnetic field, and the amount of deflection is greater when the mass of the positive ion is less, when the charge on the positive ion is greater, when the velocity of the positive ion is less, and when the strength of the magnetic field is greater. So they adjust these things to actually get a good reading at that detector. So if all of the ions are traveling at the same velocity and carrying the same charge, the amount of deflection is given a certain magnetic field is going to be dependent on the mass. And this is what they rely on to determine the relative abundance of the isotopes. So it's the mass to charge ratio. In that detection phase of the mass spectrometer, ions that reach that detector cause electrons to be released in an ion current detector. So the number of electrons reached changes the amount of current produced, and that amount of current is proportional to the number of ions that strike the detector. That detection, that peak, or that current, is linked to an amplifier, and it converts that current into a peak, and that's going to be shown in what we call the mass spectrum. Here is what a mass spectrum looks like, and specifically this is for magnesium. So at each ion of magnesium I get 3 peaks. So this first peak is my magnesium 24. This second one is magnesium 25, and the third one is magnesium 26. The height of the peak gives me the percent abundance. So here 80% of magnesium is the magnesium 4 isotope, 10% is the 25 isotope, and 10% is the magnesium 26 isotope. In all of these, actually in all the masses on the periodic table, they've used carbon-12 as the standard. The atomic mass unit, that AMU, is defined as exactly 1/12 of a carbon-12 ion. So they just, carbon-12 isotope. So they just use carbon-12 as a reference point for the mass of all elements. So here's an example of the isotopes for boron. You can see that boron has 2 isotopes from the 2 peaks shown. 2 peaks in the mass spec equals 2 isotopes. From those isotopes, we can get the relative abundance by reading off the scale. Oh, I didn't mean to do that, but here. By reading off the relative abundance. Sometimes it's also given on top of the peak. The mass to charge value is given as well. That would be this 11 and 12 that you see here. To calculate the average atomic mass of boron, you would take that m to z value, multiply it by the percent abundance, do the same for the second isotope, and then you would get the relative atomic mass of boron at 10.2. The average mass, and this is the atomic mass that we talk about from the periodic table. Okay, that's the one with the decimal. We deal with a large amount of atoms and molecules, so we use average masses in the calculations. And the average mass of an element is calculated by taking the weighted average of all naturally occurring isotopes. Okay, and then that's just the mass spectrum for boron.